Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, today we are going to learn about negative exponents and how they work, and the procedure for dealing with negative exponents. So let's just get right to it. Earlier in this chapter, you learned how to write large numbers in scientific notation. Astronomers use those large numbers to measure great distances in space. Not all scientists work with such a large scale, however. Some scientists use very small numbers to describe what they measure under a microscope. In this lesson, you will continue your work with exponents, and then you will turn your attention to using scientific notation to represent these very small numbers. All right, so first off, stoplight problem. What's the word I'm looking for? Common mistakes that students make. Let's take a look at each one of these examples. We've got 6 examples here that are going to use the different properties that we've learned so far. 2 of the problems below are correct, and 4 contain errors. Expand each original expression to verify that it is correct. If it is not correct, please identify the mistake and simplify it to find the actual correct answer. Okay, so I would like for you to pause the video for a moment, long enough to complete this problem. Copy down each one of these and expand them out and verify that this expression here, once simplified, is equal to this expression. Is this one simplified equal to this? And I would highly recommend that while you're doing it, review your notes for exponent rules that we've been working on so far, and just check and see, does this appear to be correct? All right. So go ahead and pause it, and when you are ready to see the answers, unpause, and I will do the reveal. All right, hopefully you've got everything recorded neatly in your journals. First off, x to the third times y squared times x to the fourth. If you were to expand that out, you would see, let me just get rid of that right there, that you have a total of 1, 2, 3, 4, 5, 6, 7 x's being multiplied together. That's what that says right there. And 2 y's being repeatedly multiplied together there. So this is actually correct. When you are multiplying powers together, you take the powers that have the same base, you keep your base, and you add your exponents. 3 plus 4 is 7. And y squared had no one to combine with. So yes, that is absolutely correct. So then when we move to b, 2 to the third times 2 to the fourth, well, that would be 2 times 2 times 2 times 2 times 2 times 2 times 2. That is not equal to 2 to the 12th. So this is not correct. The correct answer was 2 to the 7th power. For c, if we expand it, it's how many 7s are across the top, how many 8s are across the top, how many 7s are across the bottom, and how many 8s are across the bottom. See that you got 2 7s and 3 8s on the top. You got 3 7s and 2 8s on the bottom. So looking for your giant ones, I've highlighted the giant ones. What you may consider doing is like canceling out common factors, because every time we do that, you're essentially canceling out a giant one. So what you're left with is 8 over 7, which is what they're saying that the answer is. So they have done it correctly. Same thing for D, basically, is what we did for B. If you expand that out, you would see that you've got 5 threes being repeatedly multiplied times 2 threes. So that should be not 9 to the 7th power, because you're supposed to keep your base. It would be 3 to the 7th power. So this is not correct. You're not supposed to multiply the bases together. It's you keep your base and you add your exponents. So they did a good job of adding exponents. They just forgot and multiplied the bases. All right, so 6 squared on the top and 6 to the 5th power on the bottom. So it looks like, is that 6 to the 3rd? Well, first thing, 6 to the 5th is greater than 6 to the 2nd. So this answer actually should be a fraction. It should not be a power like this. So if we go ahead and write that out in expanded form and then cancel out the common factors, you'll notice everything canceled in the numerator, but we still need to consider a 1 in the numerator when everything else cancels out. And then in the denominator, you still have those 3 6s being multiplied together. So this is supposed to be 1 over 6 to the 3rd, not 6 to the third over 1, or just plain 6 to the third. And then the last problem, z to the third divided by z to the third is 0? No. Whenever you take a number and you divide it by itself, it is always equal to 1. So that, yeah, that doesn't work. I mean, if you think about that, when everything gets canceled out, it's just all one big giant 1. That's the answer, not 0. We're going to get a little bit deeper into why that's, well, we'll just get into it a little bit deeper as we get into and learn more about today's lesson. All right, so rewrite each expression in a simpler form using the patterns you have found for rewriting expressions with exponents. If it is reasonable, write out the factored form to help you. And I think all of these are pretty much reasonable. Okay, so once again, we're reviewing exponent rules. This particular property has us multiplying two powers together. This has us dividing powers. These two both actually are combined properties, where you are taking the power of a power as well as the power of a product that's inside the parentheses. Since 5 times x squared represents a product, there's a process we're supposed to use there. Okay, so go ahead, copy these down, and then see how well you do at simplifying, and unpause when you're ready for the answers to be shown. Alrighty, hopefully you did a good job. Let's see how you did. Well, 2 to the third times 2 to the fourth, if you expanded it, would have a total of 7. 2's multiplied together. Now, if you use the exponent rules, you would see that when you're multiplying two powers together, you keep your base and you add your exponents. So 3 plus 4 is 7. So our answer has to be 2 to the 7th power. You didn't have to expand it out. And nobody really wants to expand these out. If this was 20 to the 30th power times 20 to the 40th power, you would not want to expand it out 70 times. So we want to remember the rule. When we're multiplying powers together that have the same base, you add your exponents and you keep your base. That is the property that is called product of powers property. This is what we would call the quotient powers property, where you're dividing two powers that have the same base. And since multiplying and dividing are opposites of each other, you're going to find kind of an opposite process for getting to our answer. So yes, if you wanted to expand them out, you could. 8 2's across the top, 5 2's across the bottom. You could go and cancel out all the giant ones, or you could just use the shortcut that says when you are dividing powers with the same base, you're going to keep your base and you're going to subtract the exponents. And more specifically, you subtract the exponent of the denominator from the exponent of the numerator. But you know what I'd like to think of is this. It's like, okay, you have more 2's on the top or on the bottom. On the top, how many more are on the top? 3 more on the top than on the bottom. How many more is a subtraction question. So that's how I like to think about this process when we're dividing. But once again, it's just something you have to memorize over time. And if you can visualize it expanded out and then visualize all of those giant ones canceled, then that would leave you with 3 2's repeatedly multiplied on the top. So 2 to the third power is your answer. All right, both of these are convoluted because they use both the power of a product and power of a power property. So picturing it expanded out, you can show it like that, where 5x squared is what's the quantity inside the parentheses, and you got 3 of those repeatedly multiplied. So you should have 1, 2, 5 to the third power and x to the 6th power. Or you could think of it this way. When you take the power of a power, you will take every factor inside the parentheses and apply that. No, I'm sorry. The power of a product property says you're going to take each one of those factors on the inside there, the 5 and the x squared, and then you're going to apply this exponent to each one of them, right? Because you had 5 to the third power and x squared to the third power. And then the power of a power property says when you are taking a power to another power, you'll actually multiply the exponents. Okay, so once again, something to try and memorize, but the more times you do it, the easier it becomes. And if you can visualize it expanded out, it helps you remember whether you're supposed to multiply or add those exponents together. So 5 to the third x to the sixth is the simplified form of this. And you could say that this is 125 x to the sixth power, but they specifically say write your expression with exponents. So I'm leaving it as 5 to the third. All right, and then problem D, 4x squared with the parentheses around the 4x means you're going to apply the exponent to the 4 and to the x, and then 5x squared, this exponent only applies to what it touches, so it doesn't apply to the 5. So this is literally 4x times 4x, right? We're taking this quantity and squaring it, so we're multiplying it repeatedly twice, and then the 5 doesn't have the 2 attached to it, so it's going to just stay as a 5, but the x becomes x times x because it's x squared. So now, how do we deal with this? Do you want to multiply 4 times 5, 16 times 5, or do you just want to call that 4 squared times 5 times 1, 2, 3, 4, x to the fourth? You can do it that way, or if you just don't like this 4 squared times 5 and you just want to change it to 80, feel free to do that. I would warn you, if that said 4 to the 20th power times 5 to some other power, you would not want to write that in standard form. You would leave it as powers. So it's okay to leave it as powers now. All right, so there's a review of all of our properties for exponent rules that we have learned so far. And you can bet these types of problems are going to show up on the chapter test. So we want to make sure we have these mastered. Now, let's look at patterns for negative exponents. And we're going to start with powers of 10, then we're going to go to powers of 2, and then we're going to see if we can generalize a rule for how we deal with negative exponents. Okay. So, Salvador was studying microscopic pond animals in science class. He read that amoebas were 3/10 millimeters to 6/10 millimeters in length. He saw that whatever those are, euglenas, are as small as 8 times 10 to the negative second millimeters. But he did not know how big or how small a measurement that was. He decided to try and figure out what a negative exponent could mean. So your task is to copy down this in your journal. And what we are going to do is we are going to work our way through this to see if we can notice the pattern, okay? So take some time to copy this down first. Then I'm going to do a reveal, and I'm going to actually go, yeah, no, I guess I'll just copy this down. We'll go from 10 to the third to 10 to the negative third, okay? So take some time to copy down what you see right here, and then I will help you fill in these gaps right there. All right, you done copying that down yet? Hopefully you are. If not, you're going to have to pause and wait for me, okay? So I recreated it over here, and 10 to the third power, oh, let me just do this. That's very nice, and I'll do that. Good, good, good. All right, so we all know that 10 to the third power literally means 10 times 10 times 10, or it's equal to 1,000, right? Because it's got 3 zeros. 10 squared is 10 times 10, which is 100. Now notice, by reducing our exponent by 1, that resulted in 1 less 10 being multiplied in. So in essence, you could say that we have gone and taken and divided this by 10 to get to this. That's what they were showing up here. As you go down, with each power, you're taking your number in standard form and dividing it by 10. So if we continue that with our pattern, then 10 to the first would have to be 10, right? Since 100 divided by 10 is 10. And what is 10 divided by 10? If you said the answer is 1, then you are correct. And this is a justification for why 10 to the 0 power is equal to 1, because it follows with the pattern that we've been using so far. And so that pattern has to continue all the way up to 10 to the infinite power and 10 to the negative infinite power, okay? So I'm going to get more into why anything to the 0 power is equal to 1. But right now, let's just stick with the pattern. So if our pattern always is divide by 10, 1,000 divided by 10 is 100, 100 divided by 10 is 10, 10 divided by 10 is 1, What's the next one have to be? It has to be 1 divided by 10, which would be 1/10. If we put 1/10 into decimal form, that is 0.1, right? 1/10. So 10 to the negative first is equal to 0.1. And if you look at the place value chart in the front of the classroom, you will see that the tenths place in the place value chart is equal to 10 to the negative first. And if you're not in the classroom and you just Google a place value chart, you'll see the same thing. Hundredths place is labeled as 10 to the negative second. Why? Because 1/10 divided by 10 is the same as 1/10 times 1/10, right? Which is 1/100th, or in decimal form, 0.01. And then if you take 10 to the negative third power, you would get 1/100th divided by 10, which is going to give you 1/1000th. Which, if you think about the pattern here, notice what is happening here. Our base is 10. Our exponent tells you how many times to repeatedly multiply your base together. Look at what we did with 10 to the negative third. We still repeatedly multiplied 3 times, but we're not dealing with the number 10 anymore. We're dealing with 1/10. So in essence, we're taking 10 to the negative first and flipping the base to its reciprocal, and then whatever the absolute value is of that negative exponent, that's how many times we're multiplying it repeatedly together. Okay, so there is a pattern here, and we are going to reveal a process that you can always use to change a negative exponent so that it has a positive exponent with the exact same value. Okay, but let's not go there yet. Oh, I never finished the process. Questions I never answered. How is 10 to the second related to 10 to the negative second? Well, notice here is 10 to the second, that is 100, and this is 10 to the negative second, 1/100th. So what do you notice is the relationship between those two numbers? If you said that they're reciprocals of each other, that is the correct answer. That is the key to going from a negative exponent to a positive exponent that has the exact same value. They are reciprocals of each other. So what type of numbers did the negative exponents create? Did the negative exponents create negative numbers? And the answer to this is no, absolutely not. This is really important for you to understand. Whether your exponent is a positive or a negative number has no bearing on whether or not your answer in standard form is positive or negative. Negative exponent has nothing to do with the sign of your number. The base does, but not the exponent. With negative exponents, you get decimal or fractions as opposed to whole numbers from your bases. Okay? So the negative exponent, there's a process to convert your base into a decimal or a fractional number, not into a negative number. People are going to make this mistake a lot. Even after hearing me say this 20 times, they will still make this mistake because it's very common. Okay? The negative exponent does not make your number a negative number, as you can see down here. Okay? Now let's do the same pattern, but let's do it with the number 2. And let's start with 2 to the 5th and actually take it all the way to 2 to the negative 5th so you can clearly see the patterns. Okay? And pause. Do the exact same thing that we did in the previous. Notice how they told you that 2 to the negative first is equal to 1/2. Go ahead and continue with this process all the way down to 2 to the negative 5th. Unpause when you're ready to see the answers. All right, let's see how you did. I'll get you out of there. Let's take 2 to the 5th, which is 2 times 2 times 2 times 2 times 2 would be equal to 32, right? Since 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. As we decrease, remember that pattern, as we decrease our exponent by 1, we will divide by the base, which in this case is a 2. So 32 divided by 2 is 16. 16 divided by 2 is 8. So 2 to the third is equal to 8, because in essence, basically, you are taking away a 2 that's being multiplied, which is the same as dividing. 2 squared is 4, 2 to the first is 2, and in keeping with this pattern, if we keep always dividing by 2, 2 divided by 2 is 1, so 2 to the 0 power has to be equal to 1 according to this pattern, okay? So now it says here that 2 to the negative first power is equal to 1/2. Well, remember what we did on the previous page? If 2 to the first power is equal to 2, then if we take the reciprocal, that's going to be 1/2. So 1/2 to the first power is the same as 1/2 to the first power is the same as 2 to the negative first power. That's what I'm trying to say. So in keeping with that pattern, 2 to the negative second would be 1/2 times 1/2, or 1/4. 2 to the negative third would be 1/2 times 1/2 times 1/2, which is 1/8. 2 to the negative fourth would be 1/2 times 1/2 times 1/2 times 1/2, which is 1 to the 16th. And then 2 to the negative fifth would be 1/2 to the fifth power, which ends up being 1 to the 32nd power. Okay, so take a look what we're doing here. If we take any number to a negative exponent, that's going to be equal to the same number to the positive exponent. It's going to be the reciprocal of that answer. So 2 to the negative fifth is going to be the reciprocal of 2 to the fifth. And the reciprocal of 2 to the fifth is 1 over 32. So what question shall we answer here? Blah, blah, blah. Look for patterns. How are the values to the right of the equal sign changing? Is there a constant multiplier between each value? And yeah, they're changing because all the values are being divided by 2. That constant multiplier of 2, if you're going in one direction, becomes a constant multiplier of 1/2 when you are going, when you're decreasing the exponent, because multiplying times 1/2 is the same as dividing by 2. All right, so in problems 75 and 76, we saw 10 to the 0 and 2 to the 0, both simplified the same value. What was that value? Well, anything to the 0 power is always going to be equal to 1. Write that down, put stars and fireworks and whatever. It's a very important concept to understand. So let's look at some different examples here. If you take, well, this example, 10 to the 0 power is equal to 1. If you recall, when we were talking about the property for, when we take the quotient of powers, you recall that we would, hold on for a second. Hold on. Let me do this in the right order. If you recall, anytime you divide a number by itself, it's always going to be equal to 1, correct? 10 divided by 10 is 1. 100 million divided by 100 million is 1. 234 divided by 234 is equal to 1. Okay, so anytime you divide a number by itself, it's always equal to 1. Now, if we go back and think about this rule we learned about dividing powers with the same base, we learned that you will keep your base and you will subtract the exponents. So this becomes 10 to the 4 minus 4 power. And 4 minus 4 is 0. So if this equals this and this equals that, this has to equal that kind of a thing. 10 to the 0 power has to be equal to 1, and this rule proves it. Okay, let's try it again with 2 to the 0 power. We're saying it's equal to 1, correct? Well, if I just make up a division problem, 2 to the 7th divided by 2 to the 7th, you're dividing a number by itself, so the answer is 1. But then if we review the rules for the quotient of powers property, where if you're dividing two powers that have the same base, you're going to keep your base and you're going to subtract your exponents. 2 to the 7 minus 7, 7 minus 7 is 0, would be equal to 0. So if this equals 1 and it also equals 2 to the 0 power, then 2 to the 0 has to equal 1. So it does not make any difference how ridiculous your base is. If it is raised to the 0 power, it is always going to be equal to 1, no matter what. Right? So if we take, let's make up a number here, 22. So if you take square root of 21x cubed divided by the square root of Oh, wait, no. Hold on. If you take the square root of 21x to the third raised to the power of 22 and divide it by the square root of 21x cubed raised to the power of 22, then this quantity, square root of 21x to the third, is going to be 22 to the, it's going to be that, whatever. You get what I'm talking about, right? This has turned into a mess. Let's just erase this out of there, and trust me when I give you these examples that it always works. Okay, so back to this statement right there. Any number raised to the 0 power, no matter what your base is, it's always going to be equal to 1. All right. Noak and Salvador are looking for ways to calculate values with negative exponents without extending a pattern. Looking at the expression 5 to the negative second, they each start to simplify in a different way. Salvador thinks that 5 squared is 25, so 5 to the negative second must be 1 over 25. And Noak thinks that 5 to the negative second power is actually 1 over 5 to the second power. And I forgot to draw my box there, so you see the answer. Which student is correct? The answer is both of them are correct, because these two expressions are equal to each other. So this is the big rule for negative exponents. Rule for negative exponents. Go ahead and copy all of this down. To simplify a power with a negative exponent, first, rewrite the base as its reciprocal. I should have put a then there. Then change the exponent to a positive number. So this would be the algebraic way of showing that, where a is the base and n is the exponent. Having a negative exponent, we would just take our base and flip it over to its reciprocal, and then change your base so that it's a positive instead of a negative. So here we go. 4 to the negative third power would be the same as 1/4 to the third power, which, if you think about that, 1/4 times 1/4 times 1/4, you're going to have 1 times 1 times 1, so you're just going to get 1 in the numerator. But in the denominator, 4 times 4 times 4 is 4 to the third. So this is the power of a quotient property on display here, where you apply the exponent to the numerator and to the denominator, but 1 to the third power is still just equal to 1, so we seldom will ever write that in there. So we'll just leave that as a 1. Okay? So this is the rule for negative exponents. We now have learned about 0 and negative exponents in this lesson and why we get the answers that we get. Now it's time to start applying those, and we will begin the application of those tomorrow. Okay? Let's go ahead and move on to our next activity. Take care.
Hey, feeling good, like I should. When in dark, walk